Okay, so let's work this example of calculating pressure versus depth. And in this problem, we were asked to calculate the pressure, the atmospheric pressure in Fort Collins. Fort Collins is an elevation of 1590 meters. And so what we're going to do that is we're going to utilize the fact that at 0 meters, the height of 0 meters in our atmosphere, we have our standard atmospheric pressure. And that value is 1.01 times 10 to the 5 pascals. So we're going to utilize that to calculate the pressure in Fort Collins. Okay? So basically the sort of the reasoning step we need to make here is that the pressure at sea level is the pressure in Fort Collins. In other words, the pressure from the column that goes all the way up to the top of the atmosphere. Okay, it's the pressure of this section of the atmosphere plus the pressure due to this column here. This column that has some height D, we're calling it here. Okay, so in other words, atmospheric pressure, that is our sea level pressure, we're calling P atmospheric here. That's the pressure in Fort Collins plus the pressure from this column of height D here. And the pressure from this column of height D, as we've seen, is going to be density of air times G times D, times the thickness of that column. Okay? So therefore, the pressure in Fort Collins is atmospheric pressure minus rho GD. Okay, we just subtracted this from both sides of the equation. So therefore, when we calculate this, the pressure in Fort Collins, atmospheric pressure at sea level is 1.01 times 10 to the 5 Pascal minus the density of air, and we're given a density of air as 1.29 kilograms per cubic meter. G is 9.8. And then the thickness of this column, D, is 1590 meters. Okay? So we do that calculation, you find the Fort Collins pressure, atmospheric pressure, is 8.09 times 10 to the 4 pascals. And that's 80% of the sea level atmospheric pressure. Okay? So about 80%. And that's not too far off from the actual value. The actual value is it's about 83% in Fort Collins. So pretty close to what it is in actuality. Okay, so that's part A. Part B, we are asked to calculate the height in the atmosphere where we have half of sea level atmospheric pressure. So we're going to need to erase this stuff here. Okay, I didn't really need to erase this. This is still going to be useful. Okay, and so what we're interested in the height in the atmosphere, or the elevation, and this height is going to be here at height H, where we have atmospheric pressure, where we have 1/2 of our sea level atmospheric pressure. Okay, so this is our, we're changing this now to H. Okay. All right, so to do this problem, to figure out this height here, where, well, again, the pressure at sea level is going to be equal to the pressure of this whole column above our height H, plus the pressure from this column of height H. Okay? So our sea level atmospheric pressure, then, is equal to our pressure at our height h. We'll just call it this right now. Pressure at height h, whatever pressure when you're standing here at this height h, plus the pressure from this column of height h. So plus rho gh. Okay? Okay, now, our atmospheric pressure then is equal to this pressure. Now, what is this pressure? We're told it's half of atmospheric pressure. Okay? Plus rho gh. Okay, so we can start plugging in numbers here. Atmospheric pressure is 1.01 times 10 to the 5. So that equals atmospheric pressure, half of that for this term here, plus rho gh. The density of atmosphere, again, of the atmosphere is 1.29. G is 9.8 times our height h. So after a little bit of algebra, subtract this from both sides of the equation. Then you got to divide by this and divide by 9.8, and that gives you your height h. And that height h is 3990 meters, which in terms of feet, which we're more familiar with, is 13,100 feet. Okay? Now, this is a little far, kind of off of what our actual pressure, where we have half of atmospheric pressure. The actual value is more like 18,000 feet. Okay? So why the discrepancy? Okay, well, if this is the height where, so what we've assumed in this problem is that the density is the same throughout the atmosphere. The density is on the surface of the Earth is exactly the same as it is at the top. And that's a reasonably good assumption for liquids, which are incompressible. But gases are compressible, so the density of gas is actually higher at the surface of the Earth than it is in the top of the atmosphere. So basically what's going on in the atmosphere then is that, well, if this is the height in our calculation where we have half of atmospheric pressure, that means the pressure would go to 0 at twice this, or 26,200 feet. So that would be the very top of our atmosphere in this model of constant density. But actually, the density drops by half every 18,000 feet, and it extends well above 26,000 feet. So as a result, the actual pressure at 13,100 feet is more like 59% of sea level. Okay, instead of 50%, it's more like 59%. Okay. Because the atmosphere actually extends much higher than this particular model really suggests. So in this model we adopted, where it's constant density with altitude, the atmosphere would end at 26,200 feet. That means that summit of Mount Everest, which is at about 30,000 feet, would be above the atmosphere. It would be out in space, basically, where there is no atmosphere. But we know there actually is atmosphere on Mount Everest. People climb Everest all the time. They survive. So really, at the top of Mount Everest, the pressure is actually about, let's see if I can space over here, about 30% of sea level at the top of Mount Everest. And again, that's because the atmosphere really extends considerably higher than just this 26,200 foot level. So in reality, the density just slowly goes down with altitude. It's not constant with altitude. And that's how you explain these differences from what we're calculating with this very simple model in this problem.